Everyone, welcome to our next video, and this is going to be the last video of acids, bases and salts. So in this video we'll be discussing about what are salts, the pH of salts, and along with it the chemicals that can be derived from our common salt. Common salt means NaCl. So let's get into it without wasting much time. So let us begin our discussion with the pH of salts. Now pH of salts, as I mentioned earlier, is neutral. So pH of salts is neutral because it forms from acid and base. So acids and base react together to form salts, and this sort of reaction is called a neutralization reaction, where the acidic and the basic components neutralize each other to form salt and water. Okay, so this salt is neutral as we have studied earlier, but there is a catch to this. You see, this neutrality depends on what sort of acid and base we have. So if we have a stronger acid, then the salt is going to be acidic. And if we have a stronger base, then the salt is going to be basic. So suppose we have a weak acid and that's reacting with a strong base, then we will have a basic salt. Okay, then the salt is going to be basic because we are combining a weak acid with a stronger base. If we do the reverse, that is, we have a stronger acid combining with a weak base, then the salt is going to be acidic. And this is going to change the pH of the salt. So if it is basic, the pH is going to be greater than 7. And if it is acidic, the pH is going to be obviously less than 7. On the other hand, if we have the strength of acidity and basicity as same, if the strength of acidity and basicity of the base are same, in that case the salt that will be formed will be neutral. So that's why it will be called a neutralization reaction. So I hope it is clear that it totally depends on the strength of the acids or base. So if we have a stronger acid, which I have mentioned already, a stronger acid will give us an acidic salt, a stronger base will give us a basic salt. And if the strengths of the acids and bases are same, then we will have what is called a neutral salt, where the pH will be equal to or closer to 7. So that is about the pH of salts. Now let us move into a very interesting thing, where how we can derive different chemicals from our common salt. The common salt means NaCl, sodium chloride, that we use every day in our dining table. So how can we use this common salt to derive different chemicals? So let's dive into that. So starting off, we have sodium hydroxide. So sodium hydroxide can be derived from sodium chloride. Now if you remember the formation of sodium chloride, if you have forgotten that, so in that case what we did, we had an acid called the HCl. So we had one HCl and we had sodium hydroxide. So we had one strong acid, strong base, giving us NaCl and water. So that was the formation of NaCl. Now we will use this NaCl for the formation of other compounds. And the first compound is sodium hydroxide. So let's see how we can form that. So for this reaction, we need one electrolysis chamber, means we need an electrolytic reaction. So what we will do there, we will take one solution of salt, and the salt is going to be our NaCl. So we will have one NaCl solution, aqueous solution in water. This NaCl solution in the presence of water, and then we have to pass electricity through it. So that's why it is an electrolytic reaction. So we will pass electricity through this, and on passing electricity, this will combine to form NaOH, and along with this Cl2 and H2. So three compounds are formed by mixing these two. That is, and this solution, where you have sodium chloride, that is the salt in water, the mixture of, or the aqueous combination of salt and water is called the brine solution. This together is called the brine solution. Okay, sodium chloride in water is called brine. So in this brine solution, what we do is we pass electricity, and as a result we have we will be able to break it down into sodium hydroxide, which is our base, sodium hydroxide along with chlorine and hydrogen gas. So these two will be gases. So some additional information: for using this process, we will need one electrolytic chamber. So it is like, it happens to be like this, one chamber where you have a solution, and in this solution you will be adding NaCl, and it will be having obviously water. So this is the brine solution which I have mentioned. So this is the brine solution. So in the brine solution we will be having electrodes. Electrodes means metals through which we will be passing electricity. So one of them is going to be positively charged and the other is going to be negatively charged, and they are going to be connected to some battery. So these things you will understand after you study chapter 12. So once you are good with chapter 12, you will be able to understand what these symbols mean. This is the symbol of a battery. Okay. So now the thing is, this positively charged electrode, this is called an electrode. Both of these are called electrodes. So this positively charged one, in case of electrolytic reactions, okay, we will get into some other stuff later on, but as of now, in case of electrolytic cell, this is a cell, means a battery where you have two electrodes. So in case of electrolytic cells, the positive one is called the anode. Okay, this concept will change for other types of cells, so we will get into that later. And the negative one is the cathode. Okay, remember, for electrolytic cells only. So what happens, since the chlorine that will be formed, now chlorine is a combination of Cl minus and Cl minus ions. So these are negatively charged ions, and negatively charged ions are attracted towards the positive ones, so positively charged compounds. So since this one is positively charged, so the chlorine gases or the chlorine compounds will come here and they will react to form the Cl2. Okay, that's why chlorine is formed near the positively charged electrode, that is the anode. And in case of cathode, since it is negatively charged, this hydrogen gas is formed near this, because hydrogen gas is formed by the combination of H plus. I hope that's clear. So H plus is positively charged, so it will be attracted towards the negative one. So here we will have all the H plus combining together, and these will be giving us H2 gas. So H2 gas is formed near the cathode and the Cl2 gas is formed near the anode. So this is just for additional information, just to understand which compounds are formed in this electrolytic chamber. So all the gases will be bubbling out and you can collect them using equipments or apparatus that will come in handy in this case. Okay, so our main focus is on this reaction where we have salt in solution, which is called the brine solution. In the brine solution, we will pass electricity to decompose these two to form sodium hydroxide, chlorine and hydrogen. So this is the reaction of how we can form sodium hydroxide from NaCl. So that is the first compound that we are forming using this. Now we have one gas called chlorine. So we will use this gas to form our second compound. So if I react sodium chloride with water, I form chlorine. So I will use this chlorine for our next compound. So let's see what our next compound is. The next compound is bleaching powder, and bleaching powder can be formed by reacting calcium hydroxide, or what we call slaked lime. So if we react slaked lime, which is calcium hydroxide, with the chlorine that we produced from the first reaction while forming sodium hydroxide. So we will take the chlorine from the first reaction and we will have our calcium hydroxide, which is CaOH twice. Okay, so this is also called the slaked lime. The common word is slaked lime. So we combine these two and what we get is CaOCl2 plus H2O. And this CaOCl2 is called the bleaching powder. Now the thing is, this is how we generally represent the bleaching powder, but the composition of bleaching powder is much more complex and we will not get into that right now. For us, CaOCl2 will be sufficient to understand how bleaching powder is formed or what is bleaching powder. So bleaching powder is formed how? By reacting calcium hydroxide with chlorine. And how to get this? Means why we are saying that we are deriving bleaching powder from sodium chloride, common salt? Because this chlorine we can form from the sodium chloride. So when we form sodium hydroxide, we will form one chlorine gas. So we will take that chlorine gas and we will react it with calcium hydroxide. So combination of these two will give us the bleaching powder, which is CaOCl2 along with some water molecules. Now this CaOCl2 has various functions. As we all know, bleaching powder can be used for bleaching clothes, different fibers. Also it is used for used as a disinfectant for purifying water out of their germs and all that thing. Also this bleaching powder can be used as an oxidizing agent. If you remember oxidation reaction means a reaction in which oxygen is gained by some compound. So the term I used here is oxidizing agent. What does an oxidizing agent mean? Oxidizing agent means a compound that can donate oxygen. So it will be helping oxidation reaction to take place. So suppose compound A wants to get oxidized, suppose compound A wants oxygen to get oxidized to AO, means the oxygenated compound, which is the oxygen. So compound A undergoes oxidation. So now the thing is, it must get the oxygen from somewhere. So any compound that will be donating the oxygen for this compound to get oxidized will be called the oxidizing agent. So since CaOCl2 contains one oxygen, so this bleaching powder, this compound will be able to donate the oxygen. So CaOCl2 can donate oxygen to some other compound and help them getting oxidized. That's why it is called an oxidizing agent, means it helps in oxidation. Okay. So this is about some of the uses and how bleaching powder is formed. The next one that we will be looking into is the baking soda. So let's see how baking soda is formed. So baking soda is a very common compound that you found in our kitchen and baking soda is a compound which is very commonly found in everyone's kitchen, and we use it for our crockery, for cooking stuff and all those things, for baking anything, cakes or any other stuff, or bread. So this baking soda is actually the chemical compound that we studied earlier, and it is the sodium hydrogen carbonate, if you remember, NaHCO3. This compound is actually the baking soda. So now let's see how we can form baking soda from sodium chloride. So this is a long list of reactants that we need here. We need the sodium chloride, we need carbon dioxide, we need water, and we need ammonia. We need 4 reactants to form one compound, which is sodium hydrogen carbonate. Although the compound is not the only, this is not the only compound formed. First we form one ammonium chloride, which is another salt, and along with it we form this NaHCO3, which is our baking soda or sodium hydrogen carbonate. This is our baking soda. So baking soda, how to form? We will need sodium chloride in the presence of water, carbon dioxide and ammonia. So 3 more reactants along with sodium chloride. When they react together, they come up with the formation of these 2 salts. This is the ammonium chloride. Along with it, we have baking soda formed along with that. So this baking soda, whenever we apply it to any food item, so during cooking, what happens is, when we apply the heat, this NaHCO3 will break down into NH2CO3, which is the sodium carbonate. So from sodium hydrogen carbonate, it converts to sodium carbonate, forms water and carbon dioxide along with it. Okay. So these are the components that are formed after this has been heated. So when we apply some heat, this delta is the delta means heat, is the symbol of heat. So this is obviously not balanced. I think twice of this. Yeah, now it is balanced. So these are the reactions that happen when we just heat baking soda. But if we want to create baking powder out of the baking soda, so we need any sort of acid. And acid means a proton donor. Okay, so if I have NaHCO3, which is our baking soda, and we have a proton donor, means any acid that will donate this proton. So this combined will be the baking powder. Okay, and when we heat baking powder, what we form is again Na2CO3 and along with it carbon dioxide and water. So if you remember, whenever we apply so this is the baking powder. If you remember that if we apply baking powder while making cakes or breads, we have that fluffy bread or the fluffy cake, and we have some pores on top of the cakes or bread. So these pores or this fluffiness is because of this carbon dioxide formed. This carbon dioxide formed from the baking soda, so we need to heat it. Obviously, we put it inside that oven and we heat it. So this heat that the oven generates will allow this baking powder to break into these 3 compounds, and out of these 3, this carbon dioxide will help. Means when the carbon dioxide is formed, it is a gas, so it will try to escape from the cake or the bread that you are forming. So when it tries to escape from the bread or the cake, it will make those pores at the top and it will make the bread fluffy. So because of the air molecule, means a gas molecule forming inside the cake or the bread, it becomes fluffier and the pores are formed so that the carbon dioxide can escape. So these are very general things. I think we have studied about this earlier. So this is how the chemical reaction takes place. What chemical reaction undergoes the process that we are talking about, the fluffiness of bread. So this is all about baking soda. we have another type of soda called the washing soda. So let's see how washing soda is formed and what are its utilities. So the sodium carbonate that we formed in our previous reaction, that sodium carbonate is now going to be in action. So we will have sodium carbonate, which is Na2CO3, and we are going to react it with water. So if we have 10 molecules of water, then we are going to react 10 molecules of water with sodium carbonate. And what the reaction that we get is something like this. It is Na2CO3 dot NH2O. So for some of you it may be new that what sort of component is this, what compound is this, where you have a dot 10H2O. So these are the compounds which are actually crystals. Crystals means there is water of crystallization. So what do I mean by water of crystallization? If you have seen crystals which get dissolved in water, suppose copper sulfate crystals, if you apply copper sulfate, if you take the copper sulfate from the box and take those crystals out, you understand crystal obviously. So if you take the copper sulfate crystals and put them in water, they dissolve. So these copper sulfate crystals or this sodium carbonate, this is also a crystal like the copper sulfate crystals. So crystals are what? These are compounds that contain water molecules solidified around them. So we can form crystals by solidifying the water molecule around some compound. So this crystallization of water, what happens here? So we have sodium carbonate and we have this 10H2 means water molecules, and what we are trying to do here is we are trying to form crystals. And how to form crystals, you will learn this in in classes 11 and 12, and you will be doing experiments where you are to form some crystals of different compounds. So the thing is, what happens here is these 10 water molecules will get bound to this Na2CO3 and will form one crystal of Na2CO3 where there are 10 molecules of water present. Okay, this is called the water of crystallization. This compound which is added dot 10H2O, this dot 10H2O is actually called the water of crystallization. Means this is helping to form the crystal of Na2CO3. If you dissolve it in water or if you heat it, this water molecule will go away and these will become some dry powdery substance. So in this form, Na2CO3 in dot 10H2O, in this form it is a crystal. But if you just heat it and allow this water molecule to escape because of the heat, it will become a powdery substance just like Na2CO3, sodium carbonate. There is a difference between a powdery substance and a crystal substance. The difference is that a powdery substance does not contain any water molecule, but a crystals, for any crystal compound, if it is a crystal, it means that it has some water of crystallization attached to it. So the number of molecules of water will vary depending upon what the compound is. For Na2CO3 or sodium carbonate, it can bind 10 water molecules around it. And these 10 means if I have a sodium carbonate molecule here, it can bind 10 water molecules around it, and as a result 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if this is our Na2CO3, these are our H2O. So it is like the sodium carbonate is at the center and the Na2 and the water molecules are all around it, packing it to form a crystal. So that is how a crystalline compound is formed. This is a crystalline compound. Okay, so crystalline compound is our washing soda, and that is why it is very easy to dissolve this in water as well. And washing soda is used for washing purpose. It is used for removing the hardness of water, and we will get into hardness of water and all that in the later chapters that we are going to discuss, and we are going to discuss it very nicely. So as of now, just know this reaction, that what actually happens here. Here the sodium carbonate will react with water, and this water is going to stay as a water molecule. It is not going to combine with Na2CO3. It is just going to get attached to Na2CO3 and form a crystal structure. That is what is washing soda. And we will get into details of this along with others with the examples of some other compounds. So let's see what it is. I hope you are all aware of the compound called plaster of Paris. So plaster of Paris is that compound which is used generally if you have a fracture in your hand or your leg. The doctors give one casing of plaster of Paris over your hand or legs so that you can't move it. So this plaster of Paris is actually having this water of crystallization in its structure. Plaster of Paris is basically a calcium sulfate. This calcium sulfate containing water of crystallization along with it. So it is half H2O. We'll get to why it is half. So this compound is called the plaster of Paris. It is a powdery compound. In the form of powder it stays. Now, these are crystals. Obviously, these are crystals, but seems like very powdery substance. Now, this calcium sulfate dot half H2O, the plaster of Paris, when you react it with gypsum, sorry, I'm extremely sorry, when you react it with water, so this calcium sulfate CaSO4 dot half H2O, the plaster of Paris, reacting with water. Here we write 1.5 just to balance out the equation. What we get is CaSO4 dot twice H2O. This is another crystalline form and it becomes a solid mass. So this is the plaster of Paris and this is the gypsum. If you have seen false ceilings that people use in their houses, these false ceilings are actually boards of gypsum. This gypsum board is used for using as false ceilings, and these false ceilings are formed from what? Formed from plaster of Paris. Now, plaster of Paris contains this half H2O, and along with it, if you dissolve the plaster of Paris in water, it becomes a very hard solid mass. This remains as a powdery substance, but when you dissolve it in water, it becomes a very hard solid mass because of the combination of more water molecule and formation of this water of crystalline structures. Is containing this H2O molecule bound to the CaSO4, this calcium sulfate. So this becomes a very hard substance called the gypsum. So whenever you are using plaster of Paris to form any sort of model, suppose you are forming a human skeleton using the plaster of Paris, so you will dissolve it in water. Once you dissolve the plaster of Paris in water, it automatically converts from the plaster of Paris to gypsum, and this gypsum is the hard structure. The final hard structure that is formed by using plaster of Paris is actually the gypsum. Now what you might be wondering is why it is half H2O. How can we even have a half molecule of water? It is not possible. So we don't have a half molecule of water, and we don't even add 1.5 molecule of H2O. You can't break water molecule into half a molecule. So what happens here is actually we have calcium sulfate, and along with it we are saying we have half H2O. We don't have half H2O. Actually what happens is, if there is one H2O bound to this H2O actually contains one H2O molecule binds two calcium sulfate molecules. So if I have for two calcium sulfate molecules, I must have one H2O, but unfortunately I can't have it. So I want to show one calcium sulfate molecule. So in order to show one calcium sulfate molecule, instead of writing one, we write half, which is actually not half. You will never find calcium sulfate with one molecule of water. No, there is always going to be two calcium sulfates accompanied by one molecule of water. One calcium sulfate, one molecule of water will never be formed, because it is not possible. These two are bound together with one single molecule. They share this water molecule. So in order to just write the chemical formula, we write half H2O, but practically it is not the case. We have two calcium sulfate containing one water molecule. That's why we write this. In order to balance it out, we are writing 1.5. It is actually not 1.5. Practically something else occurs, but theoretically, just in order to write a balanced equation, we are writing half and 1.5 molecule, because you can't even break any molecule into half a molecule. It will not remain that molecule. If I break water into half, it will become H plus, OH minus, or something else will be formed. You can't break a molecule to form half of it. So that's all about how these hydrated or crystalline forms of compounds are formed. These are also called hydrated compounds. So gypsum is actually hydrated calcium sulfate. Hydrated means these H2O molecules are attached to form a crystal structure. Just like in earlier case I showed for washing soda. Washing soda is actually a hydrated form of sodium carbonate. So these hydrated compounds are formed where water molecules just stay attached to the our core compound, whatever the core compound is. If it is calcium sulfate, then in calcium sulfate you will have water molecules bound to them to give it a crystalline form. This is all about what substances that we can form from sodium chloride, and also these crystalline structures, plaster of Paris, water crystalline compounds. So everything we have now discussed about the chapter acids, bases and salts, and we have come to the end of this chapter. So if you have any confusion regarding any topic, please do comment in the comment section. I will be there to help you, and if needed, I will be making one new video based on your queries. So this is all about this chapter. Hope you liked it, hope you enjoyed, hope you understood. So that is the most important part. So see you in the next one. We will be starting our next chapter very soon. So hope to see you there. So until then, cheers.